Good morning. I am Krishna Kumar from Krishna's Classroom. Today we take up one of the very fascinating theorems, namely the primary decomposition. This is in fact a generalization of the ideas we have been pursuing. We were in search of what are called simple transparent representations of linear transformations. We found that there is a class of such linear transformations, namely diagonalizable operators, in which case we get a wonderful simple representation, namely the diagonal representation. There are situations where this may not work, and we have even characterized the situation, the diagonalizable operators, in terms of the structure of the minimal polynomial associated with this. And in fact, it is so fascinating that you are able to extract so much out of the properties of certain polynomials associated with this. Where the characteristic polynomial is the key to the whole, and then you have a minimal polynomial associated with the linear transformation. And we proved last time that if the minimal polynomial of T is the product of distinct linear factors, then T is diagonalizable and vice versa. So this is a necessary and sufficient condition for diagonalizability, namely that the minimal polynomial associated with T can be split into product of linear, distinct linear, that distinct is very important. Then we also explore situations where you may get the linear in the splitting of the characteristic polynomial into product of linear factors. Accordingly, the minimal polynomial also would split into the product of linear factors, but we cannot have a situation where they are distinct linear factors. So in that case, of course, diagonalization is not possible. Categorically, that it is not possible. And in such a case, we considered a way of constructing a representative matrix in the form of what is called triangulation. So such operators become triangular. In fact, we found that triangle, if the minimal polynomial is the product of linear factors, not necessarily distinct linear factors, then T is triangular, and this is in fact which characterizes such linear transformation. That's very interesting. We have built up a certain machinery. Using that machinery, we proved this result. Now, suppose the minimal polynomial does not split up to linear factors. Is it still possible for us to get a simple, transparent representation for polynomial transformation? So this is the question that we are going to address. So let us just briefly note down what we have. Okay? We have proved that one P is diagonalizable even polynomial E is the product of discrete and this E lambda equal where E is a real polynomial and discrete zeros occurs. Suppose T is the diagonal. Then T is triangular if and only the minimal polynomial E lambda minus where not necessarily 1. If they are all 1, then you are in case 1. We have case 1. That is the scenario. But here important thing is that this P splits product of linear and we don't use the word distinct here. If it is distinct, then it is already diagonal. But diagonal diagonal, remark. So that is the sum up of what we did so far. Our exploration stands here. Now the question that we take for our further analysis is this. Suppose the minimal polynomial P does not split as the product of linear fields. So it's still possible to this is the question that we are going to explore. So in this talk, we are going to explore this, and we end up with what is called a primary decomposition theorem. So we have a lot of insight from the analysis that we pursued so far. We consolidate all that and then finally try to answer this particular question. Okay, so let us start asking or working out the details. Now, first thing that you observe is this. Suppose P is some polynomial, not necessarily, it has nothing to do with the ET or anything, some polynomial over a field F, then there is something called the primary decomposition of the polynomial P in the field with respect to the field F. What does it mean? P can be written as the product of a set of polynomials or something of this form, P equal to some P1 to the power R1 where none of the PI's can be, but they are not firstly polynomial. There could be situations where they are firstly polynomial, and we will come back to this particular case. But suppose they are not. You can have a scenario like this. Then, see, these PI's are no more reducible in F. This is the assumption that here. So this is the ultimate reduction of PI's that we can achieve. You cannot anymore write a PI as a product of polynomials of lesser degree. Okay? So let us look at that situation. And there are examples where this happens. And in that case, what do you do? First of all, how do we come across such situations? As it is clear, if f is not algebraically closed, then you may end up with the situation that P is the product of the type I have written here, where PI's are not further reducible, and degree of each PI may be greater than 1. They are no more reducible over F. That is one scenario. Okay. The other scenario is, obviously when F is algebraically closed, then you see that, all the roots of P are in that particular field, and therefore you can write P as the product of linear lines. So these two scenarios can arise. The scenario 2 we have addressed already, and we may look at in depth in the light of the primary decomposition theorem. Look at a more structural design. That we will do. Okay. So this is something that can happen. So let me just write down these situations where we may come across this. Okay, so this is what we have. So the situation is the following. T may have a we have seen examples for this. Now, this means that is the minimal polynomial this is one side of it, or still more than T may not have a minimal polynomial which splits into product of factors. That is, if there are some linear factors, then there are some corresponding eigenvalues. That is our okay. Therefore, we cannot have all its eigenvalues, or we cannot have sufficiently many eigenvalues. That is, so you see, this is in general, this is on account of an deficiency in F. So that is F may not be, that is F is not algebraic. You know that this is because if F is algebraically closed, then any polynomial splits into product of so suddenly this anomaly comes from the fact that F is not arbitrary. We will give some example then. Okay. The other scenario is we are going to, okay, that means see, even if the characteristic polynomial splits into the product of linear factors, there may not be sufficiently many eigenspaces whose direct sum would be the whole of, or there may not be sufficiently many eigenvectors which span V. This is one problem. Second problem is that leads to this particular case. V is not eigenized. So this is the other scenario. So even if F is arbitrary, we may not have enough eigenvectors of V spanning So you see that in this case, of course, if it is algebraically closed, then it splits into linear factors. Where the characteristic polynomial splits into linear factors, all the n roots are there, some of them not certainly equal. But you find that you don't have enough eigenvectors of this kind. And you see that then we are that is in that case, how will it goes? Yes. That's it. This is the question that we have. Let us explore. The first thing is to explore some example and then get some idea of what happens. Okay, let us take something. One, two, three, four, five. So we explore the following example. First, do the usual thing that we do. We take the lead into R. Dimension is 3. Then we have B, the ordered basis sequence 1 plus square, and not only here, just define one. 6 plus 4x square x equal to minus 3 minus x minus square and gx square equal to minus 3x minus 3. Then, of course, we go for that and then extend it linearly to the mode of B. Let's clear how to define it several times. This is another case. Now what I want to do is to show you what exactly we do. How do we possibly successfully learn this? Okay. Now you see that is for the matrix representation P with respect to B, which you call B, defined B, is given here. This is the representation. Wait. The characteristic one, right? Is given by this is the ultimate splitting that you can get, because you cannot split this anymore. Because in R, you see the zeros of lambda square plus 1, there are no zeros in R. We have to go to C. Okay, the algebraic notion of R. So this is the problem. The problem comes from the choice of the deficiency on the part of associated field. Okay. Let's keep it as this. In this case, you can show that the minimal polynomial that is the ultimate splitting that is possible in R. Now let us extrapolate from our experience of working with diagonal dissection. What did we do? See, in the diagonal sliceable operators, we had P coming as lambda minus lambda 1. What did we do? We looked at the following subspaces of P, namely, we defined Wi as null space of and then we found that in the diagonalizable case we have E equal to okay. Then we got P diagonal and you have a matrix form which is has all diagonal elements or every diagonal element as one of the lambda. This is the scenario that we have. Accordingly, if you were to just mimic this, what you were to do, you would look for the following subspaces. W1 defined as null space of S. And W2 corresponding to the ultimate splitting of P that you have in the particular field. Okay. Now, the questions that you asked is this is the first question. Is V equal to these are the questions that you ask. If you have an affirmative answer for all these questions, then we see that V can be broken up into Rx sum of using subspaces, and consequently, as we have observed earlier, that you get the matrix representation reduced into a block. There is a 2 by 2 block and a 1 by 1 block appearing. Let us feel it, experience it, and then use it. Now you see that look at instead of working on t square plus I on the polynomial space, we can work with A. So we have from which you can easily go back to null space of what is the matrix? The matrix is 5 minus 5 0. It needs some work because you have to first compute A square and then add I2. I hope you do the computations. This is the null space. Now a moment's inspection of this transformation sitting inside, you will see that the rank of this is equal to 5, which implies that is dimension of W1 is equal to similarly, but this is the other part is different. Dimension of W2 equal to dimension of T1. This is equal to 1. Because you see that A minus 2I is equal to this 4 minus 3 minus 2 4 minus 3 minus 3 minus 5 this is so you see that nullity of so we get these results. Therefore, you see that you can easily check that 0, therefore you have so this breakup is available, and this is a direct sum breakup. These are all simple computation. And in fact, further deeper analysis. The basis for construct basis so these two things together this is for null space and this is for, you can see that this is an eigenvector. That is, this is an eigenvector belonging to the eigenvalue. So this forms a basis. Okay. Now, if you were to compute the representation in terms of this transformation, as we do in the usual, what one gets is the following. And if we show that representation, T gets represented in this way. Suppose see, then let us write down what are the, so W1 is spanning. And W2 can easily see that in some work, a lot of computations involved, you can easily see that with respect to the new basic that matrix minus 2 minus 3 0 and 0 0. This is the thing. It goes into block. There is a 2 by 2 block here. There is a 1 by 1 block. So this is the representation. Where D prime is of course I just write down this. Where of course D prime is polynomial 1 plus x. That's our analysis. Corresponding to what I wrote down. Then it breaks down into this. Okay. Cross check everything. Okay. So I think I will stop here. I will go to the projections, etc. offline. Okay. So what I want to do is now introduce the so-called general primary decomposition. Therefore, what our experience suggests is what? Suppose P or a of the form E equal where EIs are distinct reducible polynomials. When we expect P to be Wi to be null space of And in that case, we should get, or we expect now you can talk about projections on W1, W2, etc., Wk, and then the breakup of T in terms of these projection operators. That we shall explore this, and we shall, once you have this, so we define D to E equal to A, then B equal to now define projection. Pi from, as usual. So such projections are going to give a breakup for the whole of then Pij equal to and we also get the following, namely that T can be broken up in terms of this theorem etc. So and if Pi is the projection, it's a restriction only. Then now this is the general version. Now we shall state the theorem and then write it. So let me just state the primary difference. Primary decomposition. Let P be the minimal polynomial and P equal to where PI's are the distinct irreducible polynomials and Ri are positive. Let Wi null space of V equal to each Wi is third statement is that if Pi is the operator increased by P all Wi that is right the even polynomial Now, before we prove this theorem, which we shall possibly do in the next lecture, I want to make some statements about some results in problems which are crucial to this what we discuss. Now you see that what is this? Let us recall this because I think you already know it, but still it will be worthwhile to recall. To feel at home when we discuss it. First of all, you see this primary decomposition. This primary decomposition is very much like the primary decomposition of what we call integers in terms of what are called prime factorization. So it's a prime factorization. So if f is a field, a non-scalar monic polynomial in fx, non-scalar monic polynomial can be factored as a product of monic primes in fx one except for the of the order and only one. This is analogous to what you call the prime factorization theorem that you have for integers. You can write it as the product of prime numbers and their powers in a unique way except for the order in which they appear. So there is one and only one such breakup that you can have. Here, depending on capital F, you get the monic polynomials. So there are some prime polynomials which we, in terms of which we are going to write every polynomial. This is a very general decision. It has nothing to do with the minimal polynomial. So minimal polynomial comes along. So given a non-scalar sum of the monic factors may be then f is of the form f is of the form f1 to the power n1 etc. f1 to the power n1. The important fact is that none of these fi's can be further reduced and written as a product of monic polynomial of lesser order. So this is the ultimate level to which one can. That's the important thing. This is something like, suppose you have a, say, some number like 100. Suppose you want to mix it up as a product of what we call the prime numbers. How does it come? See, you can write this as 2 square into 5 square, or as 5 square into 2 square. But this is a unique representation in terms of the powers of prime numbers, irrespective of what order in which it is. The only thing is there are two representations possible apparently. One is 5 square into 2 square and the other one is 2 square into 5 square. But certainly you see they are considered the same, so there is a unique representation of this kind. There's a similar phenomenon here. So the prime numbers, the position of prime numbers is taken up by what are called monic polynomials, through which cannot be further split in the F. This is something that we should realize. And this is called the primary decomposition of so every monic divisor F is then of the form F1 to the power F1 where of course 0 less than or equal to these are the only devices of monic devices. So that's another result that we required. And this implies something about the GC. We'll come back to this theorem next time and do this. We also report certain facts about this representation. And that implies the greatest common divisor, GC, of a finite number non-scalar 1 point. Yes. Should I make a mistake? Yeah. Yes. It's a plain one. I'll combine. All those prime, all those small primes. Okay. The application of the factorization. That's about the GC. This also we shall go. The exponent to which each prime factor is to be taken is the largest for which the corresponding prime power is the factor of each we also observe the following. See, to understand all this, we go to what is called the prime factorization of numbers. This is just unparalleled. So you see the polynomial theory and the number theory aspects of integers. The ring aspects of integers, they go parallel. So the inspirations are not for polynomial theories. In this context, I think you can look at Einstein's algebra, abstract algebra. There's a zeroth chapter which we see, number theoretic results, which gives a lead to what you can expect at the level. That we recognize. So if you have, so if no prime factor is a factor of itself, So this is the definition of concept of relative to the context of concepts. Now with this basics, I think we should feel comfortable about the way in which we do this theorem. In fact, I don't want to just slightly lengthy, which may take some time to cover up. So I will do it in the next part of it. So, in the next part of the lecture, I will explore the good diagram. Okay, thank you very much. Stop.